Hello dear students, I am Dr. Moinuddin. Students, this is the third part of thermogravimetry, and in this part we are going to conclude this thermogravimetry. Dear students, if you didn't watch first two parts about thermogravimetry, then you must have to watch them first, because we have discussed there the basic introduction of thermogravimetry. We have seen the history, then definition of thermogravimetry, then a brief discussion on thermogravimetric curve, then the principle of TGA, then schematic diagram of apparatus, and then we have discussed a complete instrumentation of TGA. But in current video, we are going to discuss thermogravimetric curves in detail by taking the examples of two compounds, and they are calcium oxalate monohydrate and copper sulfate pentahydrate. Furthermore, we will discuss about the applications of thermogravimetry, and in the end we go to see the limitations of TGA. So the first curve which we have selected to discuss thermogravimetry is of calcium oxalate monohydrate. Here's the formula of calcium oxalate monohydrate, and you can see here is the curve, TGA curve for this compound. You can see here are the two curves. One is the thick line curve, while other one is the dotted one. This thick line represents the thermogravimetric curve, while this dotted line curve shows the DTG curve, means derivative thermogravimetric curve. And here are the conditions of the run of this run, that is 12.85 milligram of calcium oxalate monohydrate was taken as a sample. It was taken in platinum crucible, and the temperature programming was 20 Kelvin per minute, means the increase in temperature was 20 K per minute, and the atmosphere was nitrogen. So if we see the curve, so there is temperature on x-axis, you can see going to increase this way, and on y-axis there is mass percentage. So let's see thermogravimetric curve. So we can observe clearly that there is gradual depression in the weight as temperature is increasing. So with the increase in temperature, the weight is going to decrease and decrease. So it's a kind of a staircase curve. You can see it is just like a staircase. So at all depressions, definitely there is some change. There is some loss in mass which is going to happen in the compound, and definitely we are going to see this one. And how much mass is lost, we'll do the calculations by using this DTG curve, which will be shown in the next slide. And what are the chemical changes in these gradual depressions? So we can say in the first depression there could be change, and that is shown over here by the chemical reaction. So this is calcium oxalate monohydrate, and at the first depression actually there is loss of one water molecule, and what is left behind? The calcium oxalate without water molecule. Then we increase the temperature, it goes smoothly, and then there came the depression. And what gonna go happen over there? There is the removal of carbon monoxide further, and calcium oxalate that is converted into calcium carbonate. Then there is third depression over here, and what chemical changes gonna happen over there? So let's see. Actually there is the decomposition of calcium carbonate, and that is decomposed into calcium oxide and carbon dioxide. And due to removal of these vapors, water vapors, and these gases which are carbon monoxide and carbon dioxide, so definitely there is gradual loss in mass. So how much mass is lost? So we are going to see it in the next slide. So here are the calculations of mass changes by the increase in temperature of calcium oxalate monohydrate. So the first depression, if we talk about this, so since first loss starts around 100, you can see in the curve, so we may consider the loss of water. So we can write down this equation that the water is removed from here. And now we are going to calculate the percentage loss. So how can it be calculated? The mass of substance removed, the mass of the lost component divided by total mass of the compound multiplied by 100. So since here one water molecule is being removed, so mass of water is 18 AMU divided by total mass, molecular mass of the compound calcium oxalate monohydrate, that is 146.1, and multiplied by 100. So this gives 12.3%. So in first step there is the loss of mass by 12.3%. okay, then we increase the temperature and finally we reach about at 500 degrees centigrade when there happened another depression, mean another change. So calcium oxalate, that is converted into calcium carbonate by the emission of carbon monoxide as gas over here. So here is the lost molecule is carbon monoxide, and the molecular mass is 28 divided by the total mass multiplied by 100. So total removal, total lost mass here in the second step is 19.2%. okay, then we further increase the temperature and we reached around 700 to 800 degrees centigrade, at which there occurs the decomposition of calcium carbonate, and that is decomposed as into calcium oxide and carbon dioxide. So here's the calculation of percentage loss mass. So carbon dioxide, the molecular mass is 44 divided by total mass multiplied by 100. So in this step total mass loss is 30.1%. One more thing I want to include here, that the products obtained here, either they are gases or solids, should be characterized by other analytical methods such as X-ray diffraction may be used for solids, and other chemical tests may be used for gases, or even we can use evolved gas analysis. So what is the total loss of mass? So this percentage, and this mean these three steps loss will add this one, and the total loss percentage is 61.7%. Initial mass of the sample was 12.85 milligram. So final mass which were left over here, that is 4.92 milligram. So the second example of TGA curve which we are going to see here is of copper sulfate pentahydrate, and here's the curve. Here's the condition, here are the condition of this run. You can see the mass of the sample was 10.6 milligram, the crucible was made up of alumina, and the temperature programming was 10 Kelvin per minute, and the atmosphere was air, I mean air was fed inside. And here is the curve. You can see almost all, this is also the staircase type of curve. One thing must be noted over here. If we perform this experiment at, what do you say, increased temperature, what do you say, if the temperature increased very rapidly, so the events can be merged into each other. So these events can be better resolved from each other if we increase the temperature slowly. So you can see here are the two depressions, and these are quite resolved from each other. So here's the one depression, then here is the second, then third, and here is the fourth depression over here, means loss in mass with increase in temperature. And here are the possible changes which we can understand going in this compound with the increase in temperature. So in first step, it is expected that with the increase in temperature there is the removal of two water molecules, and the copper sulfate pentahydrate that is converted into trihydrate compound. Then in second step, this trihydrate is further heated, and again there is the removal of two molecules. Sorry, here 2 is missing, so you must understand here are the again 2 water molecules, and we get copper sulfate monohydrate molecule. And then in third step, copper sulfate monohydrate molecule, when it is heated, so this single water molecule is removed and we get copper sulfate. In these 3 steps, these water molecules are lost in the form of vapors. And in the 4th step, when further heating is continued, so this compound is decomposed into copper oxide, cuprous oxide, and sulfur dioxide, and half water molecule, and both of these gaseous products will be lost from from the instrument. So by using DTA curve, we can get quantitative information. So in the first step, around 100 degrees centigrade, so there is a loss of 2 water molecules from copper sulfate pentahydrate. So here is the calculated percentage loss, and what is this? 2 water molecules mean 36 gram per mole divided by the molecular mass of this copper sulfate pentahydrated molecule multiplied by 100, and that gives 14.42%. So this percentage was lost in the first step over here. Then in second step, which occurred around 160 degrees centigrade, same 2 water molecules were removed from the trihydrated copper sulfate molecule. So again there is the same removal, 14.42%. Then in the third depression, which occurs above 200 degrees centigrade, there is the removal of this single water molecule in the form of vapors. So calculated loss mass is 7.21%. And then in this final depression, what happened, which occurred around 600 to 800 degrees centigrade, so there happened the decomposition of this copper sulfate into this copper oxide, then sulfur dioxide and oxygen, and these 2 gases are removed from there. So their molecular mass, which is 80 divided by total mass, and that gives this percentage loss. So all these 4 steps and their percentage loss, so we'll add them, and this gives total loss of mass, and that is 68.18%. So initial mass of sample was 10.6161 milligram. So final mass which remained there, and that was 3.38 milligram. So here are some of the applications of thermogravimetric analysis. We know that in this technique we heat our sample and we observe the changes in its mass. So definitely we can determine the correct drying temperature and ignition temperatures, means at what temperature our sample will be completely dried and at what temperature it will be ignited. So we can find these information through this technique. Then we can determine the purity and thermal stability of primary and secondary standards used in titrations. Primary standards are those compounds which are in their pure form and their purity do not change with the passage of time or kept even for the long time in the atmosphere, while secondary standards are opposite to those one that their purity change with the passage of time, and both of these are used in titrations. So their purity can be determined by thermogravimetric analysis. We can find the thermal decomposition of various inorganic, organic, and polymeric compounds. Okay, we can determine the composition of complex mixture. Then we can study the roasting and calcination of minerals, in which minerals are, they get thermal treatment in absence or presence of limited supply of oxygen, and they are decomposed. So these processes can be studied in this technique. We can determine the amount of moisture in clay and soil, so it is quite clear. We can study the chemical kinetics of reactions, means we can find the rate of reactions, and we can study the energy of activations through this process, and we can study the solid state reactions through TGA. Here are some of the limitations of this technique. First one is, it's only applicable to solid compounds only, mean only solid compounds can run in this technique, so definitely it will become the limitation of this technique. And next one is, as thermocouples are kept very close to the sample but not in contact with sample, so exact temperature cannot be measured. We know that thermocouples are temperature sensors. They sense what is the temperature of the sample, and they are kept very close to the sample but not in contact, so definitely the temperature measured by them is not the exact temperature, so this could be the limitation of this technique. So dear students, here we sum up thermogravimetry. Thanks for watching my video. If you like it, then like and subscribe my channel, because a large number of interesting videos are coming. They are in the pipeline, so subscribe my channel, and thank you very much.